Okay, cool. Nice. I just hit the go live button.
Yeah, you see.
Yeah. All right. So thanks everyone for coming to the colloquium, especially here at Augusta University, where it's the day before spring break. So I was pretty pleased to see so many people showing up. So that's good. And today we're very lucky to have Francesco Gavazzo, or how do I say your last name?
Gavazzi, it's fine. You spell it
Okay,
fine.
great. I just want to make sure. And so today they're going to be talking about co-inductive equivalences for higher order coeffectful languages. And I, for one, am very excited about this as it's related to my own research. So should be pretty cool. So I'll let you go ahead and take it from here, Francesco. Thank you.
Okay. So, well, first of all, thank you very much for the invitation. So as far as understood, the audience has quite a different background. There should be also students in the audience. And so for that reason, I decided to split the talk essentially in two parts. The first one will be somewhat gentle introduction to coinductive equivalences. And in the second part of the talk, instead, we will see how to apply those equivalences to coeffectful languages. And the storytelling I chose for this talk is essentially the one of program analysis, so to say. And the idea is that we will start by looking at extensional analysis of programs, and we will see how program equivalence, and in particular, coinductively defined program equivalences are a good tool to perform such an analysis. And then we will move to modal or coeffectful analysis of programs, and we will see how to extend the techniques previously developed to this sort of analysis. Okay, so let us start with program equivalence and extensional analysis of programs. So what is program equivalence and why do we care about that? One of the possible many answers is that we are interested in understanding extensional properties of programs. And what do I mean by that are those properties that can be studied essentially by regarding programs as black boxes. And that means that we can observe programs somehow, we can observe their behavior without really inspecting the program. The program is a black box, so we cannot see what is inside the program. We can just observe the relationships essentially between the input and the output of the program. And that is the extensional behavior of the program. Now, the reason why we are interested in these properties, of course, among others, is that because they have many applications in computer science and in programming language theory in particular, of course. In particular, they're used to prove correctness of programs, to prove optimization techniques and refactoring. So let us see a couple of motivating examples. So here on the left here, we have a simple program to perform the addition, the sum of two numbers inside an option type. So inside the option types, you can have the number, and in that case, you have the sum and the number it is inside, or you can have nothing essentially because maybe the computation failed, and in that case, you have no. And this is a simple program that performs the addition of two numbers of that sort. Here instead, we have what we would like to say to be essentially the same program, which is now written using a monadic style. If you're familiar with monadic type systems, fine. Otherwise, it does not matter. Just notice that we first define two functions here, which are somehow standard way to refactoring the code. And then we define our function for performing the addition relying on these two functions. So we would really like to say that starting from this program here, we can refactor it using this monadic style. And of course, the story, behind this operation is that the two programs should be the same. And what do we mean by that? Well, it's exactly the fact that if we pass them the same input, then we obtain the same output. So as long as we use the programs in this way, there is no detectable difference between the two. And to prove these sort of things, what we would like to do is in fact to prove that these programs are extensionally equivalent. Second motivating example, this time about specification and implementation. We may consider a specification of natural numbers with their arithmetic, so a successor function, addition, multiplication, and so on and so forth. And we could also consider an implementation of that specification, this time given by church numerals, for instance. And again, what we would like to prove is that the implementation is correct. And a possible way to formalize correctness is, again, by proving some equalities between two programs. So for instance, we may prove that if we apply the successor function to a church numeral, we indeed obtain, from an extensional perspective, the next church numeral, right? So again, this is a way to formalize an equivalence, a correctness of an implementation using a notion of equivalence. Okay, so how do we deal with these sort of extensional properties? Well, there are many ways to do so. Among the most popular ones, we have the notational semantics. We have logic, in which we define logical formalism to talk about properties of programs, and many others, of course. The relevant point is that in all these approaches, what we come up with are indeed the notions of equivalence between programs. For instance, we may say the two programs should be considered equivalent if they have the same denotation, right? Or if they satisfy the same formulas. And the main features, and all these proposals share some main features that make them valid for the extensional analysis of programs. In particular, the notions of equivalence that we obtain are indeed equivalence relations, meaning that we have equational reasoning. We have compositionality, which essentially means that to study the behavior of a complex program, such as this one or this one, it is enough to study the behavior of its subcomponents in isolation. In particular, it means that if we take two programs which are extensionally equivalent, and we replace the first one, say P, with the second one, Q, in a larger programs, then the overall behavior, the overall extensional behavior of the software remains unchanged. And of course, all these notions of equivalence are coarse enough, which means that they abstract from the syntactic or irrelevant details of programs. And in particular, they just look at the extensional behavior of programs, and all other details are not considered. This is all very nice, but sometimes finding the notational semantics, finding suitable logic system may be hard, especially if your language is very expressive. And to overcome this issue, what one could do, and what we often do in programming language semantics, is to take a somehow dual approach. This time, what we try to do is to define a notion of equivalence natively on programs, with the idea that, of course, the equivalence-related programs that have the same extensional behavior or the same denotations, if you have a denotational perspective on the thing, on the whole issue. And the nice thing is that essentially you stay inside the language. So you do not need denotational semantics, you do not need logical system, you just need the programming language and its operational semantics, which I would actually consider part of the definition of the language. Using just these two ingredients, you define the notion of equivalence that you use to perform analysis. Now, of course, once you do that, you want the resulting notion of equivalence has the nice properties that we have seen before. In particular, it must be an equivalence relation, so that we should be able to reason about programs equationally. It must be compositional, which is essentially the main requirement that we would like to satisfy, which from a mathematical perspective, what it means is that we have a congruence relation. And it must be indeed coarse enough. And again, that means that what we need to have are a relation that relates programs only if they have the same extensional behavior. Okay, so we have extensional analysis of programs. We have more or less see how program equivalence, looking for program equivalence, is a good way to perform this sort of analysis. But the truth is that there is no just one notion of equivalence. It's not hard to realize that there are many of them. And so the question is, which one should we take? And to answer this question, the best way to go is to investigate program equivalence in a foundational calculus. So we pick a foundational calculus, we define some notion of equivalence on it, and see what happens if the definitions are good enough, what we can prove about these equivalences, and so on and so forth. So for this talk, and also in light of the second part of the talk, the foundational calculus we consider here is rather simple. It's a call-by-value lambda calculus with recursive types. And in particular, we choose this calculus, so we may assume to have other types like sum types or product types and whatever. But we will just focus on function types because that allows us to model high order feature of the calculus, and recursive types are there because we also are interested in modeling infinitary behavior and we want to have a Turing complete language. Now the calculus is as usual, and you have a standard big step operational semantics. So I will not talk too much about that. This is rather irrelevant. And by the way, I choose call by value because usually program equivalence is more interesting for call by value languages, but you can actually repeat all the things that I will tell you in a call by name setting. So the calculus is not really relevant. It's just a means for a goal. All right, so we pick the calculus, and immediately we notice that we have some candidate notion of equality between programs. So we have, for instance, syntactic equivalence, which, of course, without much of a surprise, turns out to be too strict. For instance, it does not even allow us to prove computational-like equalities. We also have the so-called clean equivalence, which is essentially the equivalence given by operational semantics, which just tell us that two programs are equivalent if they evaluate to the same value. So we execute them, and we require both the execution to terminate and to give the same values. Again, this seems, of course, nicer than syntactic equivalence, but we still have some troubles. It is still too strict. In fact, it is an easy exercise to check that if we go back to our previous example on church numerals, and if we try to prove that the successor of 1 is cleanly equivalent to the numerals 2, then we get stuck. Again, because the equivalence is still too strict. Okay, so what we have to do is to move to coarser notion of equivalences, and there are many of them. Again, one can use contextual equivalence, logical relations, CIU equivalences, or many others. The one we are interested in this talk are essentially forms of applicative bisimulations, of applicative bisimilarities, which are coinductive equivalences, which I choose because they have a pretty good balance between expressiveness and usability. Now, there are several ways to approach coinductive equivalences from an informal perspective. One may try to understand them in terms of labeled transition systems, in terms of experiments and observers. The approach that I will follow in this talk is the one with maybe a bit less of intuition, but with, in my opinion, a better mathematics, which in the end helps the overall understanding of these sort of things. And here the idea is that what we will do is essentially to work in the category of equivalence relations. Now, if you're not familiar with category theory, it does not matter. I will not use any category theory until the last 3 slides of the talk. The only things that matters here is that the kind of mathematical objects we are interested in are set together with equivalence relation on them. And the reason why we're interested in that object is that because we will consider programs of a given type together with an equivalence relation for programs of that type. So what we will do is essentially to associate to any type a notion of equality between programs of that type. And now the transformations that we look for between these objects are just functions that preserve the relation, so that whenever we have equivalent objects in the first set and we apply the function, we still obtain again to another pair of equivalent objects. And again, the reason is that because the kind of transformations we are interested in are actually open programs. And this condition here, that function preserve the equality between programs, is exactly compositionality. Right? It's exactly a condition that tells us that we have a congruence and that we have compositionality, which is, as you have already seen, a fundamental requirement for this whole business. Okay, so that's the framework in which we will work. And let us start trying defining applicative bisimulation by associating to each type tau a notion of equality between values of that type. So we begin with values, they are simpler. And most of the clauses are actually standard. So for instance, we say that two pairs of values are equivalent if they are pairwise equivalent. So we just look at their inner values and we require them to be equivalent. And same conditions apply to the fold of two values. We just look at the values inside and require them to be equivalent. The really interesting clause is the one here for lambda abstractions, which are just functions essentially. And what applicative bisimulation tells us is that functions are equivalent if they are so mathematically. And mathematically, two functions are equivalent if we have function extensionality, which means that we pass them an input and we obtain equivalent output, which is given exactly by these conditions here. And then we can, once we have equality on values, we can easily define equality on arbitrary terms. We just require two terms to converge to two values which are themselves equivalent. Okay, now this is very nice, very intuitive from a mathematical and a computational perspective. But the question is that, is this one really a good definition? So is this and this whole series of conditions well defined? And the answer is that, well, we have to check that. And standard approach is try to do that inductively, right? So we try to define these equalities on values first by induction. And the first attempt is induction on terms, which we immediately see that it fails, because if we want to use function extensionality, then we may come up with terms that are bigger than the original ones, so we cannot do induction. And therefore, what we may try to do is now induction on types. But again, we have the same problem. Because we have recursive types, here we may come up with a larger type. That's essentially the same problems you have if you're in an untyped setting. So how do we solve this issue? How do we overcome this issue? Well, the solution given by applicative simulation is to move to a coinductive definition, which essentially means that we transform our candidate definitions into a bunch of conditions, that any suitable notion of equality between programs should satisfy. And then we take the canonical relation meeting that condition. And in this setting, canonical means the largest relation. So let us begin with the first step. What we do, we convert previous definition into condition. So that, for instance, now we say that a relation, a candidate equality between programs, is a good one if, for instance, it is closed under function extensionality, right? So that's exactly the same definition we had before, but now we have replaced the if and only if with implications, making a condition. That's right. And then what we do, again, is to take the canonical relation to satisfy this condition. And here by canonical, we mean the largest, which we can prove by means of standard lattice theoretic techniques that exist. It is the greatest fixed point of a suitable functional, but that's not relevant for this talk. It is enough to know that there exists a largest applicative bisimulation, and it can be characterized as the union of all bisimulation. And that gives us a powerful notion. For instance, we have the so-called coinduction proof principle that tells us that now to prove that two programs are equivalent, it is enough to find a bisimulation between them that relates the two programs. So that, for instance, we may indeed now prove that the successor of one is equivalent to two by showing that this relation here is an applicative bisimulation. And I know that might look scary at first, but this is exactly the relation that you obtain, starting with these two pairs here, and then by adding, pairs that satisfying these clauses. So that's the way we go. Okay, so step back to our relational perspective. So now we have bisimilarity, and we claim that it is a good way to equate programs. Of course, now what we need is actually bisimilarity to be an equivalence relation, because here we are working with sets with equivalence relations between them, and that is the case, and that's an easy proof. And the other condition is that functions essentially preserve equality, that amounts to compositionality. And again, also that condition is met, although now the proof is more complicated. Okay, so what applicative bisimilarity is essentially what it gives us. It gives us a lightweight technique for the extensional analysis of programs. It is an equivalence and it is compositional. So it has all the requirements that we have seen to be the necessary ones somehow to indeed perform extensional analysis of programs. So, of course, this is not the whole story about applicative bisimilarity and applicative bisimulation, but I hope that somehow gives you a taste of what this equivalence looks like. All right, so what we have seen is extensional analysis of programs, extensional reasoning about programs, how we can use program equivalence to perform such a reasoning, and how applicative bisimilarity is a good notion of equality to perform that kind of thing. However, although we have seen that there are many interesting applications of this sort of extensional analysis, these are not the only ones. And in particular, what we are going to consider are the so-called modal or Coeffectful analysis of programs. As far as I know, there is no universally accepted terminology. So here we use modal and Coeffectful independently. And what are these sort of analyses? Well, these are analyses in which you have essentially two features. So the first one is that you may want to have information of what happens inside the program. So you cannot regard a program as a black box anymore. You have somehow to look at least partially inside it. And the second main feature of this sort of analysis is that now you consider the observer, so the observer that is studying the behavior of the program now has some specific capabilities. But we'll see what I mean by that in a moment. So let us begin with some examples of this modal or Coeffectful analysis. First example is information flow. Again, here what we have is a program with input and output, and now we'll actually look at whether the input or the outputs are private or public. So we have some notions of security level somehow, and we look at how the programs map these private or public input to public or private output. And in particular, here we are not just interested in what happens to the input and the output of the program, but we are actually interested in observing how the information flows through the program. So what happens when I put some private input in the program, when to understand what happens inside the program. And in particular, the kind of analysis we want to make in this scenario are statement of the form that no information can flow out of the program. So no private information, sorry, can flow out of the program. So we have put some private input and then something happens inside the program, and we want to see what happens to this private information. In particular, we do not want this information here to flow through public information, which is now observable. And second example, where we have a modal or Coeffectful analysis program, is program sensitivity. I know that you had a talk on related to this notion by Marco Gaboardi a few weeks ago. So I guess you're already familiar with these things and with its many applications to differential privacy. Just recall in a nutshell what we mean by program sensitivity. Well, what we want to understand here is essentially how much programs amplified errors in the input. So in particular, we may say that what we want to see is whether a program is, let's say, case sensitive, which means that whenever we give it input, which are epsilon apart, we want the output to be at most k times epsilon apart. And again, this is an example of non-purely extensional analysis of programs. Here, we are not just concerned with the relation between input and output, but we also want to understand what happens inside the program. So how much, for instance, it can amplify the input. Now, a first informal observation is that all these phenomena, as well as many others, such as dead code analysis or resource usage and strictness analysis, can be analyzed relationally. So for instance, if we come back to our example of non-interference, of information flow, we have the notion of non-interference, which has been introduced by Martin Abadi and collaborators, which now states that a program has the non-interference property if whenever I change a secret input, so suppose that the program has take as an input a secret key, and I change this key with another one, K2, let's say, then the result of the program is essentially the same from the perspective of a public user. And that essentially means that if I'm a public user and I observe the result of these two programs, I see essentially the same thing. So I'm not able to tell whether, by observing the output of the program, whether the secret input was, let's say, key 1 or key 2. So again, this is a sort of, this is actually an information flow analysis of programs, which is performed by in a somehow relational way, by means of some sort of program equivalence. We are still at a very informal level. And similar situations happen if you look at program sensitivity, where we now have the notion of metric preservation, which has been introduced by Reed and Pierce, which formalized this idea that a program is case sensitive, again in a relational way, by saying that whenever two inputs are equal up to an error epsilon, and we pass them to a program P, then the output should be again equivalent up to an error K times epsilon. Okay, so the moral is that we have some good intuitions, some ground intuitions, why the relational techniques should be applied, in particular program equivalence, should be applicable not only for the extensional analysis of programs, but also for the Coeffectful and the Modal analysis of programs. However, if we try to formalize this intuition, to make things a bit more in detail, then we see almost immediately that the classical relational techniques that we have seen in the previous part of the talk do not work. And that is essentially because when we look at extensional program equivalence in an extensional setting, two programs are either equivalent or they are not. An observer can distinguish them or she cannot. Here we have something different, because now the equality between programs actually depends on some observer's features. So for instance, we may have programs that are equivalent for a user, for an observer, which only has public permission. But it may not be so if now the observer has private permission, right? She has now more means essentially to test, to inspect programs, and therefore she may be able to discriminate that. And the same happens again with program sensitivity. Now we can think to the observer as having some limited accuracy in her observation, and she cannot distinguish programs which are which differs of an error below epsilon, so that the observation is not accurate enough for that. However, as long as we improve the accuracy of the observer, then the program should not be regarded as equivalent anymore. So we move from a setting in which programs are just equivalent, or they aren't, to a setting in which now the observer has an active role somehow in determining equivalence. And the features she has, permission, accuracy, resources, or whatever, determine whether programs should be regarded as equivalent or not. And there is another main issue if we try to apply classical, let's say, relational techniques to this sort of setting, namely that compositionality fails. And it is quite easy to notice. For instance, if we now pick two programs, two keys, which are publicly equivalent, so we assume, for instance, these two keys to be secret, and we should regard them as equivalent for a public user because she just does not have the permission to observe these two programs. This condition, so this equivalence here, is not preserved by if we put this program in larger programs. So for instance, we may pick a very simple program that just tests the value of the key, okay, if it is bigger than a given number C, 0, 1, or whatever you choose. And for some of these C, at some point, if these two keys are actually different, one of them will be bigger than C, and the other will be not. So in the first case, we will have that the output of the whole program here will be 0, and the output of this program here will be 1. So even an external observer, which who only has public permission, will now be able to detect differences between these two programs. And again, if we look now at program sensitivity, then the situation is even easier somehow, because now you take two programs which are equivalent up to an error epsilon, and now your program, what it does, it just simply duplicates the program. And by duplicating the program, it also duplicates the error. So obviously, the output of the two overall programs here will not be equivalent up to epsilon anymore, right? Because you have duplication. So the moral is that not only program equality depends on some observer's features, but it is also context sensitive, which means that there is no hope to achieve compositionality, as we have seen in the extensional analysis of software. Okay, so although our intuition told us that there may be some hope to approach this modal or Coeffectful analysis of programs in a relational way, relying on program equivalence, we have two main issues that seems to suggest that actually this is not the case. The first one is equality depends on the observer's features. The second one is that equality between programs, equivalence between programs is context sensitive. And so the question now is, can we really use program equivalence to perform this sort of analysis? And the answer is in the affirmative, but require us to move from an extensional setting, from a standard theory of program equivalence, to a different theory of program equivalence. And we will do so in three steps. So the first step is to move from languages with standard type system with languages with graded modal type systems, where here the intuition is that we now add to our type system modalities that give us information on how code can be manipulated. So for instance, we may say that now the piece of code is private, so it can only be used in a way that somehow preserve this feature of the code. We may say that a function now has sensitivity k. Well, that's the intended meaning, of course. That a function has sensitivity k, which means that once we pass to this function an input, then we cannot use that input, let's say, more than k times, essentially. So again, here the modality gives us at the same time information, of course, on how the code is used. Also, it constrains the way in which you can use code. Or we can also say that a piece of code is copyable, right? So give a piece of code and we are allowed or not to copy the code. So first step, we move from standard types to graded modal types. Second step, we move from ordinary relations to ordinary equivalence relations to what we may call Kripke relations, which are just equivalence relations, which now are indexed essentially by some possible words, exactly as it happens in modal logic. But now instead of dealing with proposition, now we deal with relations. And the idea is that here possible words are an abstraction of the observer features, and we may and then these may stand for the available resources. So now we consider equivalence as a resource consuming process. So for instance, we may model different hardware systems by means of resources. We may model the accuracy of the observation. So now the possible words tell us whether two programs are equivalent, given that the observer has that accuracy in the observation or security permission. And the third step is that we want to match essentially these two changes. So we want to understand what happens if we are trying to compare two programs in which now has the modal types in a given possible word. And we will do it so by introducing a notion of a Comonadic Lax Extension, which is a scary name for something that is not that difficult, but essentially it's the mathematical abstraction that allows us to model that interaction. And then will also give us a new notion of compositionality, which we will understand in a few slides. Okay, so the remaining part of the talk, the plan is to go into these three improvements somehow of theory and try to understand them. So let me begin with graded modal types, and let me also remark that graded modal types, well, very likely you know these topics much better than me. Harley is doing a lot of research on in this field, so So I guess you already have the chance to see these sort of things. The way I will use this sort of type system are essentially as a way to capture this idea that quality now is context sensitive. In particular, I will use these types to give the information of the way the context uses the type, and we use that information essentially to factor the equivalence of the programs to achieve compositionality. And for this reason, I will not give you too much details about them because they are not that relevant for understanding equivalence. We would like to stay more on the semantical side. And also because our techniques are actually, to some measure, language agnostic, which means that as soon as you have a type system that gives us this information of how the context uses the input, then you can come up with nice notion of equivalence. So for instance, it is an easy exercise to move from graded model types to quantitative types, for instance. But in this talk, I will use graded model types. I like the formalism, and also, to the best of my knowledge, they are also used in concrete programming languages, in Relational, for instance, which has graded model types natively, and they're also using the linear Haskell, where people are still doing quite a lot of research. Okay, so graded model types. So as I said here, the idea is that we consider type system that give us information on how programs are used. And that information, more concretely, give us some structural information on code manipulation. So for instance, we have modalities that give us structural information on code usage, information flow, program sensitivity, resources, and so on and so forth. And a bit more concretely, when we move from the language of the previous part of the talk, of the first part of the talk, to language with graded model types, what we do is to first change the base of the type system, so that now we move to a linear type system, which essentially means that by default, programs cannot be copied or erased. So we regard programs as resources, essentially. And then we add these graded S4 modalities, which are standard S4 modalities, which are now indexed by grade, which are also called resources or capabilities, which are elements that come from a suitable algebra. Now, before looking at the algebra, let us look at some examples of these sort of algebras. If we're interested in resource usage, we may consider these algebras here, which now give us information of whether the program is dead, so it is not usable at all. It can be used only linearly, or it can be discarded but not duplicated, or you can use it as well. You can freely duplicate and discard the code. We may consider algebras that give us information about security levels. So for instance, here we have a very simple one in which the algebra tells us if the piece of code is private or public, but we can consider richer algebras with more security levels, and everything works fine. And finally, we have the algebra for program sensitivity, which now types is decorated somehow with a non-negative real number that tell us intuitively the sensitivity of the program. So how much time how we can use the program if we want the function, the program to have given sensitivity. Now, all these algebras here can be formalized using a graded algebra, that are called this sort of algebra in that way, which are essentially pre-ordered semi-rings. Again, the details of the algebras are not really relevant. The only point to stress is that we have these semi-ring operations that essentially allow us to combine code usage. So the elements of J give us the element of the algebra, give us the way in which we can use code, and then we combine these constraints, these code usage information using the elements of the algebra, and it is used essentially for typing. Now that we have extended the type system, we also extend the syntax of the language, and so the language remains pretty much the same, but now we add constructs for introducing and using programs of model types. Again, this is not really relevant. The crucial point is that now typing judgment has this shape. And in particular, we have these assumptions here that essentially are telling us that, for instance, the program T is using the input x1 according to the grade J1. So again, J1 is the element of the algebra that tells us how the program T uses the code. And using this type system, this typing judgment, we indeed now are in a condition in which, if we regard this program here as a context, we know just by looking at the typing judgment how the context uses its input. And then the operational semantics essentially remains the same. There is nothing specific to the operational semantics. And that's actually something to notice, that the operational semantics of these languages is usually resource agnostic, which means that we have these resource, this code, usage annotation, and so on in the type system, but we do not have them in the operational semantics. And that's the reason why we will also move to a notion of equivalence, which is resource sensitive somehow, exactly because we don't have this sort of information in the operational semantics. Okay, that's the idea of graded model types. So the take-home message is that now we have a syntax of a type system that give us the information on how context uses the code. So that is the way in which we fix the second issue that we have seen before, the one about context sensitivity. Let us now move to our first issue, namely that now equality depends on some observer features, and therefore we move to Kripke relations. So here the idea is that when we are in the extensional realm of program analysis, we just have ordinary binary relations that tell us that programs are either equivalent or they're not. Now what we do is to move to a setting in which the equivalence between two programs actually depends, is given essentially with respect to a possible word. And a possible word, as you have seen, give us information, give us the observer features, the permission, resources, accuracy, and so on and so forth. Now, what are possible words? Well, in this setting, we steal ideas from the substructural, from the semantics of substructural logic. And in particular, because the calculus has a linear base, what we take as a possible words are monoidal preorder, which are just monoid with a preorder on top of that. And again, examples, that's just mathematics, but for this talk, just think about examples. What we have, well, it's very trivial, a monoidal preorder, because we have essentially no monoidal structure of security levels. So a user has either low security level or high security level. We have the one of accuracy, which again is given by non-negative real numbers. And now we have the equivalence is given with respect to an epsilon, which is the accuracy of the observation. Or we have, if we assume to have a set of resources, we can take the multi-set of that resources, which now tell us what are the resources available to check the equivalence between programs. And you can model, for instance, some hardware capabilities in that way. And now the nice things about working with this structure here is that essentially we have enough mathematical construction to mimic the usual algebra of relations. So we can mimic the standard constructions we have on binary relation, but this time on these Kripke monoidal relations. In particular, for instance, we can define the composition of two Kripke monoidal relations in a standard way, but now notice that possible words are taken into account, and when we compose relation, we need to move to a different possible word. And now, because we have all these constructions, what we can build is a category of Kripke relation, Kripke monoidal relations, which is exactly as we have seen before. But this time, instead of having sets with equivalence relations on them, we have sets with equivalence Kripke relations on them, because we have identity, we have composition, we have symmetric, so we can formalize the notion of an equivalence Kripke relation. And maps are the same. The only difference is that now everything is parameterized by possible word. So what we consider are these functions that preserve equality at any possible word. All right, so that's the idea. of Kripke relations. So we just move to a setting in which we consider equality in a given possible world. And then we want to make these two improvements, namely the shift from standard languages to grid model types and from standard relation to Kripke relations interact. And how do we do that? Well, just by defining a notion of program equivalence for languages with grid model types. Equivalence now will be, without much of a surprise, a Kripke equivalence relation. And in particular, the attempt is the standard one. As we have seen, we have a category of Kripke relations, which is pretty much as the one that we have used for standard relations. So now what we would like to do is to associate to any type Kripke equivalence relation of program of that type, right? And then consider arrows as we did before. So what we do is try to import the definition of a applicative Bisimulation that we have seen before in this modal or Coeffectful setting. Yeah? And most of the clauses are actually rather straightforward because they are just the same ones that we have seen in the extensional version somehow, but this time instantiated with respect to possible worlds. The key point, of course, is to understand what happens when we are trying to equate two programs that can be used according to J, so that they have a model type, in a word W. And the idea is to understand what happens is that model types actually do not really act on programs, they act on possible words. So again, we can look at some examples. First, if we look at program sensitivity, then we say the two programs that can be used k times, essentially, are equivalent up to an error epsilon, if and only if the programs are equivalent up to an error delta when used once, and when epsilon is bigger than k times delta. So we look at them in a possible world that tell us what happens if they use once, and then we just scale that error to k. And with security, we have something even simpler. Now we take two secret values. Now, again, we have the information given by the type, and we may ask when they are equivalent for a public user, and the answer is trivially always, because she has no right to observe these two programs. And when they are equivalent for a user that instead has secret permission, well, then you just really look inside the program here. Okay, so how do we formalize this example? How do we capture the essence of this example? Well, this is the point where you need a bit of category theory, where we need further step of abstraction. And the key observation is that all this business that we have seen about program equivalence, all these ways to define these conditions that we have used to define program equivalence, can actually be factorized as follows. So we start with a type, right? And you have a way to associate to that type a notion of equivalence for programs of that type. Now, when we come to define conditions, for instance, to when two programs of a narrow type should be considered equivalent, what we are doing is essentially to apply a construction on the type. The construction may be the product, the arrow types, or whatever. And what we do to define the conditions that define equivalence is essentially to extend this construction now to act on these equivalence relations, right? And the condition is exactly given by the construction here. So the moral is that when we try to define notion of program equivalence, we start with some construction on types or sets. And what we want to do is to essentially extend this construction on equivalence relations, right? And that gives us exactly the conditions that allow us to define notion of equivalence. And in doing so, of course, the game is that we want to essentially preserve the main feature, the main mathematical feature of the construction here when we extend it to relations. And in particular, for instance, most of the type constructions that we have are functorial. And what we want to do is now to extend the construction on to equivalence relations in such a way that the construction we obtain is functorial. And we do have the mathematics for that. This is the notion of a Lax extension, which has been introduced by Barr in the context of topology, which is just a map that allows us to extend Kripke relations. Now I've used this notation, but these are just Kripke relations to the construction F. And the map must satisfy some structural requirement, but which are just stating that the construction is functorial. And for those of you that are familiar with category theory, a Lax extension is exactly the same thing as giving a function on the B category, on the 2 category of relation. Okay, so if we take this abstract perspective, now the question is, what about modal types? So what are the relational construction that we should associate to that type? And the answer is, at least our answer is that modal types from a relational perspective are graded comonadic Lax extensions of the identity monad. Okay, that's a scary expression. So graded comonadic Lax extension just means that because we deal with graded S4 modalities, and from a semantical perspective, these are just graded comonad of suitable types, essentially. We want our construction to still induce graded comonad or relations somehow. And the fact that we actually consider not just any comonad, but the identity comonad, that reflects our intuition that modal types act on possible words only. So they do not modify programs. So the construction here is just identity. They do not modify programs. They just modify relations. They just modify the way in which the observer tries to equate that program. So, and that gave us the notion of a comonadic Lax extension, which again is a map on Kripke relation that satisfies some structural properties, which again, if you're familiar with category theory, this is giving a graded comonad, actually a graded identity comonad, essentially, on the 2 category of Kripke relations. All right, and now that we have this mathematical abstraction, we can actually complete the definition of a modal applicative Bisimulation. We have seen the previous clauses are the same. Now, the interesting thing is that when the 2 programs that are used according to the modality J at word W are equivalent, if they are equivalent, or here there is a typo, there should be no box here, just B and V prime. Still at word W, but now this time when the equality is essentially modified by the comonadic Lax extension. And what the comonadic Lax extension does is essentially to tell you how you should move from the word W to a different word in which you just compare the 2 programs. So for instance, all the examples that we have seen before about program sensitivity, information flow, all those definitions are formal that can be formalized by means of this comonadic Lax extension. And now we can, what we can prove is that we have a new notion of compositionality. Now we have all the ingredients to fix the issues that we have seen when we try to approach naively Coeffectful analysis using program equivalence. Now with these ingredients, we can come up with a different notion of compositionality, which is better explained if we look at the picture here, and this is the formal statement. Now, the statement now tells us that if we want to check whether 2 compound programs are equivalent at the word W, it is enough to look at their components in isolation, indeed at the same word W, but now the equality should be factorized, should be modified according to the comonadic Lax extension. And the comonadic Lax extension is essentially determined by the typing judgment, which indeed tell us how the context C uses the programs. So now we indeed have a context-sensitive notion of compositionality, where context sensitivity is given by the typing system. So it is a structural notion of program sensitivity, of context sensitivity. And now it is taken into account by the comonadic Lax extension that tell us how this user J, so the way in which the context uses the program, act essentially on the possible words. So on the observer. Programs remain the same. This delta here just essentially modified W and tell us how the observer changes is her resources, her accuracy, her knowledge, her permissions, or whatever. And in fact, the notion that we have seen at the beginning of the second part of the talk, metric preservation. Oh, and again, here there is another typo. Here it should be non-interference, right? Again, it is standard exercise to see that there are instances of this of our compositionality theorem, where the comonadic Lax extension are exactly the one here that we have seen before. Okay, so that concludes essentially also the third part of our plan. To go through graded model types, Kripke relations, and Comonadic Lax Extensions. And it also move us towards the conclusion. And what we have seen essentially is in a very sketchy and not that formal way that coinductive equivalences are indeed a good tool, can be extended from an extensional setting to a Coeffectful setting, and they give us a good tool to perform modal and Coeffectful analysis of programs. So there are, of course, many other approaches. So if we want to stay in the realm of the program equivalence, there is a recent work by Abel and Bernardi on logical relations for this sort of analysis. The language they consider is different than the one I considered in this talk, but as soon as you have understood these ideas, it's not hard to make comparison between these two approaches. Or you can even go beyond, outside actually, the realm of program equivalence, and you can, for instance, move to the notational semantics. And in that case, there are the works by Marco Gabuardi, Dominic Orcad, and others on the notational semantics using Comonad for this sort of calculi. What I show you is just about a small piece of our work on notions of equivalence for Coeffectful languages, and in particular, what we have is a connection between this sort of modal analysis of programs and a quantitative analysis or metric analysis of programs. And Ugo and I, in particular, have recently showed that these two analyses essentially are the same. And that meaning that giving notions of Coeffectful equality is essentially the same as given a suitable notion of metrics between programs in an abstract setting. And what I also didn't show you is how to extend this whole business to languages with effects. So up to this point, we have considered graded modalities only for code usage, but people in the literature, in the community, and also papers in the literature actually uses graded modalities also to give information about the effects that are produced by programs. And in that case, you have monadic types, and all the things that I've shown you can be actually extended to that setting. And then the idea is that as you consider Comonadic Lax Extension, without much of a surprise, there you will have a monadic Lax Extension. And that's all. I hope I didn't run out of time. Thank you very much for the attention. And if you have any questions, of course, you are very welcome to ask them.
Yeah, thank you very much. That was great. I really enjoyed this. I learned a lot. I've been wondering kind of how graded modalities would work with possible worlds. So it was pretty cool to see how you're doing that. There was one question in the YouTube chat here about an example that you gave on the slide about applicative bisimulation, where it was the pair of successor 1 and 2 example.
Yes.
They were wondering how that is different from evaluating the transitive closure of beta reduction for the program that you were given there.
Because let me find the slide. Okay, because here, because we are in a code by value setting and we are in a lazy setting, lambda abstractions are values, and we do not evaluate under lambda. So once we reach a lambda abstractions, we are done, and we have and the evaluation is terminated. If we look at the examples of church numerals, for instance, and if you take the successor function here and you apply the church numeral, let's say 1, what you obtain is that, well, you replace and here inside the code with the church numeral 1, but then you still come up with a lambda abstraction, right? And therefore, from the point of view of beta equivalence, you're done. This is a value. There is no further reduction that you can do. And now applicative bisimilarity tell us, well, the game is not over. What you have to do is to pass it an input, right? And then you obtain again a lambda abstraction. And then you tell us, okay, pass it another input, and then you obtain something that you have to evaluate. And in fact, if you look at the concrete relation that we have used to prove bisimilarity, okay, what you see is that what we have is exactly that game. So we start with the two things, and we pass one to the successor, and we obtain again a lambda abstraction. And of course, the church numeral 2 is already a lambda abstraction. Now what we do is, well, again, the game is not over. We pass it another input, which is just these clauses about extensionality. So the game tells us, pass it an input and continue the game. And we reach another lambda abstraction. So we pass it another input, right? And we obtain these sort of things here. And now when we start to evaluate it, we see that these two actually give the same programs, and then we are done because we are the identity relation inside here. Mm. So the point is that the calculus is lazy. It does not evaluate under lambda abstraction. And that's the reason why when you reach a lambda, sometimes you still have some information to exploit and you want to see that information by passing an input.
Yeah, that makes sense. Yeah, thanks. Does anybody else have any questions?
I have a small question. So thank you for your talk that I really enjoyed.
Thank you.
I really appreciate the care you take in showing that your equivalences are contextual. And I know that quite often in lambda calculus or pi calculus, people cheat a bit without always telling it. Like when you look dead in the eye, you notice that, for instance, lambda xy application dot, sometimes people say, well, that's not really a context because I'm just throwing away my term, so I don't want to look at this one.
Okay.
Do you have any restriction like that on your, or for instance, in pi calculus, people often get rid of like a dot plus p because it's like, well, it's the same thing. You're just throwing away my term or doing p, and I'm not really interested in that kind of context. And so I guess I have two questions. The first is, do you have any limitation of that kind on the first result you've shown? And the second is, in the second part of your talk, you actually showed us contexts that were problematic. Have you thought about a syntactical characterization saying, well, if your context does that, I don't want it? That wouldn't necessarily use graded type, just kind of syntactical restrictions on your context.
Okay, so for the first question, no, there is no restriction on the shape of context. I mean, we just consider any context here. Actually, I didn't give a definition of a context, just leave to an intuitive level, but you can really think it as a term with a hole inside.
Okay.
Okay. So there is no restriction on that part. Concerning your second question, yes, I mean there's been some work in which one tried to isolate the context that she considers the good ones, essentially. So here the idea is that you do not want that restriction. You want context to be of any format. But at the beginning, I mean, if you look at the literature on metric analysis of programs, because I actually discovered this work on Coeffectful and other things coming from metrics, essentially from program metrics, and there you have exactly this thing, the very same problems. So you have a distance between two programs, and you want to prove essentially the contexts are non-expansive functions. They behave as non-expansive functions, and that of course is not the case because the context may duplicate the input. And the first work that had been on that topic in the higher order setting was actually on looking just limited form of context. So for instance, a fine context. If you just pick a fine context, they can only discard programs, then you can indeed come up with a notion of distance, which is non-expansive. And the same happens here, essentially. If you just work with a fine context, then you do not need all the Comonadic Lax Extension stuff, because essentially the context has not enough power, essentially, to make equivalence really context sensitive. I'm not aware of other characterization of different families of context when one should be interested in working with. but I think that in principle is possible. That's not the spirit of this approach, where instead we want as many contexts as possible, and we want them to come with information on how they change equivalence.
Yeah, and I think it's really good, because quite often the restriction on context are like ad hoc. They're just remove the context that doesn't play well. It's like, well, why are you removing those? Well, they don't play well. Like, okay.
Yeah,
well,
yeah. Then I mean, here the whole point is the opposite, right? To consider.
Okay, thank you very much.
Yeah, thank you for your question.
Yeah, great. Was there any other questions from anyone? All right. I think I had a quick question. You were saying in the future work, you might look at how to handle effects. Would there have to be any notion of grading for handling effects in this, or would it just be, would it still just be a graded comonad that we use to kind of restrict contexts?
So that's not future work. That's something we already have. But,
okay. Sorry.
It would have been
maybe I said further.
It would have required too much time to do that in a 1 hour talk, and I think it does not really add understanding to these things about the modal analysis or the Coeffectful analysis of programs. But essentially, the idea there is that you stick with this construction here, with this picture here.
Right.
Okay, with this picture here. And now what you have, you model effects using model types, for instance, and you could consider them either graded or not. Okay. So here you have, again, construction, which now is not just functorial, it's monadic. And therefore, what you consider is this notion of a Lax extension, in which you add a couple of clauses that tell us that what you have is not just a functorial construction, but is also a monadic construction. And then, of course, I mean, you should also add some details about gradings in case you consider graded monads.
Yeah.
And that tells you how to compare programs which are effectful. So, for instance, if you take two probabilistic programs, you essentially come up with two distributions. And here, the Lax extension tell us that you have to compare distribution essentially by considering the Larsen-School lifting of relations to distributions. And now then, of course, you have two constructions at hand. You have the Comonadic Lax Extension, which is the one about how the context uses the program. And then you have the Monadic Lax Extension, which tells you which are the effects produced by the program. And you want these two to interact in a nice way. And that essentially gives us a sort of a distributive load.
That's what I was curious about.
Yeah, you have a sort of distributive load, which is actually lax. So if you take a denotational perspective on this work, on this all this business of program equivalence, you may start from the work by Marco Gaboardi, Shinya Katsumata, Dominic Orca, Flavian, and all the others, and essentially make all of these a relational model, in which the main difference is that instead of having functors, monad, and comonads, and so on, you just have lax version of them. Mm. So you have slightly less constraint, essentially. Yeah. That's pretty much the idea.
Yeah, cool. That's nice. All right. Well, if there's any last minute questions, we can take them. Otherwise, we will be done for today.
Okay. Thank you so much, Francesco, and congrats on your leaks paper.
Oh, thank you very much.
Oh, it's always a good thing.
Okay.
Great.
It has been a pleasure. Thank you very much.
Yeah, thank you. We really enjoyed it.
Bye-bye. All right. Thanks again.